All right, I got everybody's missions. I'll staple them. It's fine. Don't worry about it. It's in the back here. Thank you. Thank you. Thank you. Name?
Oh, sorry.
It's okay. Oh, okay. I'm sorry. All right, this everybody's from here? Okay. Thank you. All right. So I'll begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and this time we have to meet together, study your creation. Just pray you'd help us to use this time wisely, that we'd all learn a little bit more about calculus today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I believe I have scanned the solution to this thing, and I wanted to talk about, there's some things I marked wrong that I didn't take points off for. Not this time anyway. I just want to kind of give you, just a heads up about it, so that, hopefully it doesn't, happen again in such a way that I have to take points off. I mean, I'd rather you keep your points. I have enough. I don't need more, Let's see here if I can find it. There we go. Oh, well, I've got this thing open. I guess I'll top hat. I forgot to bring the attendance sheet today at the moment, so I know you guys like the top hat. Let's see here. Like, we spent $80 on that thing, so we should use it. Let's see here. Where were we? The magical number for today is 6587. 6587. Now, and again, if you don't do that every time, it's not a problem for me. I will try to go off the paper attendance when it comes to, like, when the sports people inevitably ask me, how many missed classes did this person have? I try to look at I don't look at top hat. I look at the paper sheet. Let's see here. So, let me get it out here. Here is the solution. So let me, before I forget about anything else, some things I'm starting to see. So, like here, for example, y, let's just make one up. Y equals x squared, e to the x, let's say it was that. And then somebody writes this, d dx equals to 2x e to the x plus x squared e to the x, right? I've seen this. What's wrong with this? Yeah, well, what's wrong with this is this right here. This is an expression. This is an operator. These are not equal. All right? Like, what you should write is this. But the y missing doesn't matter. You can't write d dx or d d theta equals derivative. This is just nonsense. All right? Don't do this. I do have to take off points, like on a test, if you do that. All right? Just so you know. So, not a big deal, but try to fix that. I didn't take points off for that on this quiz, okay? Now, the other thing, and this is an understandable problem, is like about 3 or 4 of you got to the point of simplifying, which was wonderful. But the thing is, this is the differentiation, so you need to differentiate after you've done the simplification, right? Take the next step and do the power rule. So minus 1/12, minus 12 minus 1 is minus 13/12, and 3 over 12 is a 4. 4 times 2 is an 8, and so that's what you get. Now, suppose you didn't get this. Well, that's good, because like one person here got this. Maybe 2. All right? Everyone should get this problem by the next test. Otherwise, Like, if you don't get this problem at the end of the course, I really shouldn't pass you in this class, honestly. I really shouldn't. Because if you can't do this problem by the end of the course, Calculus 2 here is going to be very, very troublesome to you. Like, it'll just be this endless cycle of taking it over and over again without passing. And we don't want that to happen. And engineering does need us to get you guys to a certain level. So this problem is something everybody can, get to a point of solving. Not everyone's there yet, and that's okay, but you need to work on that if you got that wrong, and that's pretty much everybody. Let's see here. This part, hey, a lot of people got this right. I was very pleased. There's like, I would say 50 to 60% of the class got this one right at the moment. Now, some of you don't quite know the product rule, and others of you are making up new rules of differentiation I don't have names for. But there is a good part of you who got that right, and everybody can get that right. Let me talk about it. So what we're doing is the product rule, right? So the product rule says that d dx of a function times another function is equal to df dx times g plus f times dg dx, right? That's what's at play here. And the f is e to the x, and the g is cosine x, all right? So df dx is e to the x, and dg dx is minus sine x as we derive from the difference quotient. You remember those limits? Hey, isn't that great? This is like the first time I've said limit in like a week, isn't it? Hasn't that been pleasant to not talk about limits? We should stop and appreciate that, right? They are coming back, though. There is this thing called a final. The limits will be on the final, so if you still don't understand that stuff, you need to circle back and fix it. But this one here, I'm a little bit less forgiving here if you did stuff like, and it doesn't usually people end up, what typically happens is people just write, like, this is the thing I see a lot of people do, something like this, 2x plus 7, and then 3x squared, right? I see this written. This doesn't work, okay, because that is equal to 2x plus 21x squared. On the other hand, 2x plus 7 with parentheses is what you want. Those parentheses are not like, maybe you need them, maybe you don't. Those are required parentheses. Not having those parentheses makes it a different expression. It makes you wrong, all right? So if you're skipping those parentheses, don't, all right? You need them. And I'm talking to some people, a few of you actually, who have otherwise immaculate work, like really nice work, nice penmanship. I can see what you're doing, it's great, you're just missing those parentheses. And for the person who's super neat, it might not actually hurt you because you might actually, in your mind, like, these parentheses are there, I just can't see them because I can't read your mind, I only see what's on the paper. But there's another person here who skipped the parentheses and then distributed incorrectly in the next step. All right, so we just need to use notation which is true. We need to write things which are true on our paper, not things which are an indication of things that will be true once we get through the thought process, all right? Every line of mathematics you write on the paper, you want it to be true. This is our goal. All right, so there's that. I took off like 10% for that error, not like a lot, but this one here, like a lot of you got it, not everybody. So yeah. So the thing is, secant squared minus tangent squared. Remember, we have derived the identity. I worked this out the other day that in fact tangent squared t plus 1 is equal to secant squared t, right? So that means that secant squared t minus tangent squared t is equal to what? Not 0, but it's equal to 1. And you're right, the derivative of that would be 0, right? Now, the other way to do that, of course, is just to differentiate secant squared minus tangent squared. And how do I do that? Well, this is the square function, right? So I differentiate the square function, I get twice the inside function, which is twice secant. But then I have to multiply by the derivative of secant, which is secant tangent. So lo and behold, I get a secant squared tangent, right? But the minus tangent squared also differentiates to 2 tangent times the derivative of tangent, which is secant squared, as we worked out, right? So lo and behold, you get the same term twice, but plus minus, so it reduces to 0, right? So, and the reason I put simplify there is because I don't really want to try to decide if your, quarter line thing mangled full of sines and cosines and is actually 0 in disguise. Like, you should simplify. So we should see that one's 0. Anyway, so a lot of people got the last problem, actually. I was pleased with that because I feel like you guys missed easier problems. To me, this is a harder problem, the one with theta in it. What goes on here is we've got the square root of something, so we have to do the chain rule for square root. So the derivative of square root is 1 over twice the root, and then I have to take the derivative of the inside function, which here is 3 plus theta cosine theta. So what's the deal with 3 plus theta cosine theta? When you differentiate it, the derivative of 3 is 0. The derivative of theta is 1, so I get cosine theta from the first term of the product rule, and I get the minus theta sine theta from the second term in the product rule. Of course, thinking of the differentiation as being theta, not x, of course. But anyway, some of you got this, some of you didn't. Some of you were halfway there, so I give you half credit. I don't give a lot of partial credit with differentiation. It's important that you get this. Eventually, you want it to be exactly correct. This is not a place where there's like a lot of wiggle room. You need to get this down. This is something you need to master in this course. Next page, I suppose. So here we've got a derivative of cosine squared e to the 3x plus 8. So this is one of those chain rule upon chain rule upon chain rule problems. So the outside function is the square function. So you've got twice the function, the inside function being cosine of parentheses e to the 3x plus 8. So then I have to differentiate that, at which point cosine is the outside function. And then I identify the inside function as e to the 3x plus 8. So to chain rule on the cosine of that, which gives me minus sine of that, right, times the derivative of e to the 3x plus 8. But the derivative of e to the 3x plus 8, again, chain rule, because I'm differentiating with respect to x, not 3x. When I differentiate, I pull down a 3. Because, of course, you get e to the 3x times ddx of 3x, but ddx of 3x is 3. So lo and behold, this is the final product there. I do think a couple people got this right, but most people got this wrong. So you're not alone if you got this wrong, but it's something you'd like to get right in the future. I don't think anybody in here has yet learned both of these things, this and that. Now, admittedly, I don't believe I ever differentiated cosecant in class last week, right? Well, I did not. But the reason this is a reasonable question is the same techniques we used to calculate derivatives in here is all you need to differentiate cosecant. So how do you do that? So yes, I expect you to memorize the things we've done in terms of basic derivatives like sine, cosine, cosh, sinh, inverse tangent, inverse sine. But also, you should be ready to derive things that you don't know. So here's how that goes. dd theta of cosecant theta. Well, what is cosecant theta? I guess that's the first thing. Cosecant theta is 1 over sine by definition. And so we can do minus 1 over sine squared times dd theta of sine theta. Now, what am I doing? I'm thinking of this as being dd theta of 1 over u, where u is equal to sine theta. Now, if you don't like that, when we did that to start with, we did what? We did the quotient rule for this kind of thing, like the secant derivative, we did quotient rule. I personally, for reciprocal functions, find it easier to think like this. It's not really quotient rule, it's just the chain rule with the reciprocal function. So chain rule with the reciprocal function, derivative of 1 over u is minus 1 over u squared, right? Minus 1 over u squared. And then, so what do I get? I get minus cosine theta from the derivative of sine divided by sine times sine. I'll write it this way to make it perhaps more obvious that what you're looking at is minus cotangent theta times cosecant theta. All right? Now, if you had written here like, you know, the same, like that expression, but with like, you know, if you had like cosine of 6x divided by sine squared of 6x all times minus 6, you'd be exactly correct there, and I shouldn't have taken off any points for that if you did that, okay? So, but I probably took points off for like the other half then, in all likelihood. So the other thing going on in this problem, remember we worked out that the derivative with respect to x of inverse tangent, what did we work it out? We worked this out. It is equal to 1 over 1 plus x squared, right? So if you have an inside function, a u, and inverse tangent, the way that works is 1 over 1 plus u squared times du dx. See, that's the chain rule for the inverse tangent function. Come on. Come back to us. Oh, I forgot the adapter. Let me unplug this before I show email or something stupid. Oh, come on. There we go. It's always annoying when the computer comes back on and it's like a, you know, like grades with personal information. Then I have to edit the video. It's the worst. So what's going on here, we've got inverse tangent of u, where u is 3x. So I have 1 over 1 plus u squared, which is 3x squared. What's du dx? Well, du dx is just that 3. So this is the chain rule there. Now I didn't work out again on this test why the derivative of inverse tangent is 1 over 1 plus x squared. We worked that out last week, right? I think I had a couple people get this one right. We did talk like, briefly about the triple product rule. That's what you need here. A lot of you picked up on that. That's wonderful. You just need to like carry it out more carefully. And that's fine. I have taken the liberty of factoring out this, mostly just because I'm lazy and don't want to write it 3 times. I didn't require that of you. I didn't say simplify, so I wasn't going to take off points if you didn't do that. I'm just lazy, okay, in terms of writing it. Okay, so like the triple product rule gives me this, plus that, plus that. The derivative of 2 to the x is the natural log of 2 times 2 to the x, all right? So that's why I have natural log of 2 times this junk for the first term. The second one, I've got derivative of 3 to the x squared. That gives me natural log of 3 times 3 to the x squared times the derivative of 3 to the x squared. Let me write it down here. Just a second here, guys. All right, so like derivative with respect to x of 3 to the x squared, how's that go? Well, that is the natural log of 3 times 3 to the x squared. That's the derivative for the, right, remember the general rule? If we have d dx of a to the power x, we work this out, natural log of a times a to the x, right? So applying that to base 3, I get this, but we're not done, right? Because we're differentiating with respect to x, and yet it's 3 of the x squared function, right? So there's a chain rule that's required here. We have to multiply by the derivative with respect to x of x squared. So that gives me 2x times the log of 3 times 3 to the x squared. Okay, so that's why I have a 2x log 3 right here and all that, because that's what's left in the middle term. Finally, this one, when you differentiate 4 to the x cubed, you pull down a natural log because that's derivative of 4 to the x, 4 to the u rather. And then since u is equal to x cubed, we pull down a 3x squared. So that's why I have a 3x squared times log 4 for this last term. And they are all sharing the same 2 to the x, 3 to the x squared, 4 to the x cubed, so I can just factor that out. So there's actually another way to do this derivative today in terms of what we'll call logarithmic differentiation. So maybe we'll do this example again as a lead example of logarithmic differentiation once we're done with this quiz here. finally, problem 2. Finally, problem 2, yeah. Sorry, I'm an idiot. Derive the rule for derivative inverse sinh. So we did this about 5 different times the last week or so classes, right? It's our 1, 2, 3 step 4 step process. Number 1, we write y equals the inverse function. Number 2, we solve for x by taking the function of both sides. We get x is equal to sinh y. Then we differentiate that implicitly. Notice that I never write d dx equals the thing. I have like an arrow with a d dx to the side indicating that's the operation that I did. Did you see the distinction between that and like what I was talking about earlier? But anyway. So we've got like cosh of y times dy dx by the chain rule. The derivative of x with respect to x is just 1. And then I solve for dy dx. I get 1 over cosh y. And but the thing is, cosh squared minus sinh squared is 1, which means cosh squared is 1 plus sinh squared, but sinh was x. So we get 1 plus x squared, which gives us finally 1 over the square root of 1 plus x squared is the derivative of inverse hyperbolic sine. Now there is another path that you could have gone down if you've got a much better memory than me. Like I had to look this up personally because I always forget this particular formula. But there is a formula for inverse hyperbolic sine, right? In problem 33 of mission 1, we worked out that inverse hyperbolic sine is in fact the natural log of x plus the square root of 1 plus x squared. It's in fact possible to write every inverse hyperbolic function as the natural log of an algebraic function. This can be done. There's straight up formulas for it. So if you know those formulas, you can find the derivative of inverse hyperbolic this and that by just differentiating its formula. But did you guys know the formula? No. And finding that formula is harder than the 4-step process we just went through. So that's why I don't teach this. This is the method. I don't think it's a method, but it is nevertheless curious. It's kind of neat how it works out. Like when you differentiate this, you get 1 over that. And then the chain rule gives us this. But then if you make a common denominator of like the square root of x squared, you end up with x plus the square root of x squared from that term actually. And then you've got this and that above and below. They cancel, and what do they leave you with? The 1 over 1 plus x squared. But I don't know. So if you didn't know the implicit differentiation technique, you could also do it this way. But that is a kind of special quirk of the inverse hyperbolic functions. Now, one of you, I think, didn't realize there was 2 sides to this quiz. That was unfortunate. I'm reminded of a story in grad school. I was in a quantum mechanics class, and we come out of the test, and we were like, that wasn't that bad test. He's like, yeah, I think I got all 100 points. And we're like, but dude, there were 200 points. And he's like, what? We're like, yeah, he's like, did you turn the test over? He's like, turn the test over. Oh, man. So, yeah, I know sometimes I give one-sided quizzes here. Sometimes I give 2. I always flip it over to find out if there's more to the adventure. That's one thing. Now, some of you had scores less than 5, but I feel like if you've come to class and you've made a legitimate effort, and I think all of you did, you should have at least a 5. So I curved this one up to 5. If you had less than 5, I just gave you 5. So if the numbers don't add up and you have a 5, it's because I'm like, under 5. I'll put it up to 5. Just because I really don't want these quizzes to kill your grade or anything. And I mean, it is only 8% of your grade overall, right? So if you got a 50% on them overall, you'd lose 40 points of your 1,000. But I'd really like to not see that be 50 points of your 1,000 or something. I'd really like to see it to be very little. I would love for most of you to like lose very little of the quiz grade. So that's why I put the 20% bonus on each quiz and why I'm dropping the lowest one in each 3, right? But, which is not to say that it's easy to get a good quiz grade, right? Because it's still fresh and you're still learning and there's time pressure, all these things. So, any questions? Yes, no, maybe so. All right, well. Let me show you where we are in the notes. We are, if I can find it. Huh. Come on. Just to show you, we are So any of you guys learn logarithmic differentiation in your like high school calculus course? Anybody? Nobody? Oh, I see one. One. So logarithmic differentiation is something I did not learn in my Calculus 1 course. And the reason for that is, I think I told you guys before, but my Calculus 1 was an independent study over the summer with a very nice lady doing a favor for my parents. But nevertheless, she had not done calculus in like a decade. So there were some holes. And like logarithmic differentiation would be one of those. I learned logarithmic differentiation when I was taking one of my junior level like physics courses. I had a homework study group. We have like 3 other guys I work with. And it was great. We spent probably like 30 hours a week doing homework, something like that. You guys think you have a lot of homework? You don't have a lot of homework. You just don't. Trust me, it could be much worse. So these courses were kind of the vast unknown, and like the junior level physics courses are like, I don't know, 10 times harder than the freshman ones. Don't worry, we don't offer those here, so you're safe. Not yet. Good point. I like the optimism. Let's see here. So, sorry, don't look at the screen. I forgot to tell you guys, get your Dramamine. But I guess I could have used the index. That would have been smarter. But it feels like cheating, you know? So anyway, I was sitting there, and we had some homework, and I was minding my own business, doing my differentiation, and then my friend, who I like to call Somber Paul, put down his homework and started working on some Led Zeppelin riff, which he's always working on the guitar, learning some Zeppelin, typically. And I was like, wait, what? How are you done with this problem? And he's like, what? I just used log differentiation. And I was like, wait a minute. What are you talking about? What's log differentiation? And then I learned that I was missing an important tool in my toolkit of differentiation, namely the logarithmic differentiation. Come on. All right, here, finally. So we're in section 3.11. It took me long enough. And so in here I have a bunch of examples of logarithmic differentiation and the technique. So, but I'm not going to I'm going to write it on the board. I just want to let you know, if you're following along in the notes, we're in section 3.11 now, right? So put this away here. So I was like, because Paul, like I was differentiating, I was still like mid-calculation, and he'd put his note thing down and he was enjoying his life. And I was still in the midst of another page worth of differentiation. How did this happen? It's because Paul knew logarithmic differentiation. That's how it happened. So let's talk about what is log differentiation. In a nutshell, logarithmic differentiation is using the power of the logarithm to simplify complicated derivatives. And what is the power of the logarithm? Like, what does the logarithm do for you? What's that? Nothing? It causes you pain? What are the main properties of the logarithm? Do you guys remember? So if we're talking about the natural log, chief among these properties is probably this. Natural log of e to the x is x again, right? But more interestingly, the natural log of like AB is the natural log of A plus the natural log of B. What else do we know? The natural log of A over B is natural log of A minus the natural log of B. All right? And then still also interesting, natural log of like A to the power P is equal to P times the natural log of A. So these are your basic algebraic properties of the natural log. Now, what do we need to be true about A and B in order to do this? What's the domain of the log? X has got to be greater than 0. Yeah, A and B, exactly. Now, how about the X? Does the X have to be, no. Now that you brought up the topic, what do you think about X? Does it have to be positive? It's just, this thing leaks. I've lost my other one. I need to find a better squirter thing. So annoying. So what do you guys think? How about x? Does x have to be positive? You vote yes? Any other votes? We're going to democratically decide. This is a republic. Actually, this is a benevolent dictatorship. That's the structure of my class. I mean, I try to be benevolent. No, x doesn't have to be positive because x is in the domain of the exponential. So the domain of exponential is everything. Its range is the positive numbers. That's the range, excuse me, the domain of the natural log. I'll say my words eventually here. Listen, these are lovely, but what you actually want to use is something that's kind of a little bit more greedy. So let us try to learn the following rule. If I have the natural log, and let me just do it for like 4 things, okay? I'll write it down for 4 things. Maybe if I write it down for 4 things, that'd be enough. A to the P, B to the Q, C to the R, D to the S. All right? What's the deal? How does that simplify? The way this works is you do P times the natural log of A plus Q times the natural log of B minus R times the natural log of C plus S times the natural log of D. Oops, my bad. That last one was not a plus, it was a minus. All right? Now I can derive that rule for you. How would you derive that? What are the steps? Step number 1 is that this is the natural log of a to the p, b to the q, minus the natural log of c to the r, d to the s, right? Because the natural log of a quotient is the difference of the natural log of the numerator to the natural log of the denominator. Then I can apply the other property of logs to break this up. And that gives me the natural log of a to the p plus the natural log of b to the q minus the minus parentheses are your friend. Don't let your friends down. Natural log of c to the r plus the natural log of d to the s, close parenthesis. But then I can apply the power rule for the natural log 4 times. And I get p ln a plus q ln b minus r ln c minus s ln d, which of course is what I wrote down. Was that a sneeze? That was, maybe that was like it's like Pokemon. Maybe that's its name. I don't know. Achoo! 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 Sorry. Again, I'm an idiot. But listen, I think that we can go through the steps down there for complicated expressions, but wouldn't it be nicer to write lots less and just learn this simple, let's call it a lemma. So this is an algebra lemma. A lemma is like a little truth that you can use to make bigger truths, right? It's kind of a wee bitty theorem. Would this make sense to you guys? All right, so what's logarithmic differentiation? One other thing we need to talk about before we actually do logarithmic differentiation is the chain rule. What is the derivative with respect to x of the natural log of u? How's it go? The derivative of the natural log is 1 over the function, right? So we get what? 1 over u, but since we're differentiating with respect to x, we have to multiply by du dx, right? So there you go. That's your center. So we're going to use this thing. We're going to use this over and over and over again. All right? Example 1. Let us begin with y equals to 2 to the x, 3 to the x squared, 4 to the x cubed. I would like to show you how to take the derivative of that using logarithmic differentiation. So I guess I probably should write down for you the algorithm, right? Let me write down for you guys the algorithm of logarithmic differentiation. It is a multi-step process, but the steps are pretty much the same every time. So once you do one successfully, you ought to be able to do them all. So step number one is a lot like our implicit differentiation, right? So step number one, oops, these are junk. What am I doing? Step number one, I already did. It's like step number one, write y equals to ugly stuff. So there's your ugly stuff, right? Step number two is to, and this is a little bit different, take natural log of, equation above and use lemma to simplify. Step number three, differentiate implicitly. Use chain rule for logs. And step number four, you solve for dy dx. The beautiful thing about this method, and this four-step process is logarithmic differentiation. The beautiful thing about this method is not only does it save you the trouble of learning triple product rules and stuff like that, is it automatically produces pretty simplified answers. So it's really neat. But really, we're just using algebra to do calculus better is the truth here. So all right, so we did step number one. Step number two, we take the natural log. Take the natural log of this. We've got natural log of y is equal to, let me just go ahead and use my lemma. So I've got x log 2 plus x squared log 3 plus x cubed log 4. Okay, admittedly, I just extended the lemma to a product of three things. But do you want me to write down other lemmas? Did you get my point? Like lemma number 2, if I've got log of a to the b, say I've got log of a to the p, b to the q, c to the r. Well, that would be p log a plus q log b plus r log c, right? That's how the log works. Pull down powers, and in a nutshell, what the logarithm does is it converts products to sums, right? And why is that helpful? Which is easier to differentiate, a product or a sum? Search your heart. Which is easier? Surely the sum is easier, right? The sum rule. Did anyone ever get the sum rule wrong? I'd have to really go looking. I'd have to search for 500 solutions of different calculus students' papers before I found a wrong use of the sum rule. This is a very rare Pokemon. On the other hand, if I was looking for a misuse of the product rule, I need not look long, right? 30% of the quizzes I just graded don't have product rule down right? Okay, so then what? So step 2 is done. Step 2 is done. Step 3, differentiate implicitly. What happens when you differentiate log? What he said. All right, so 1 over y dy dx. So I interpret that, what you said was use the chain rule, right? Yeah, probably? Okay. It was there. He said it. We all heard it. He said it. So 1 over y dy dx. And then how about differentiate the other side? So you guys, natural log 2, natural log 3, natural log 4, these are just numbers. They just pull out of the derivatives. They just appear alongside. So derivative of x log 2, Derivative of x squared log 3 is just plus 2x log 3. Derivative of x cubed is 3x squared log 4. All right. We have now completed step 3. Step 4. Solve for dy dx. So we got dy dx equal to y times this. Let me call this stuff Pac-Man for the sake of me not writing it again. So dy dx is y times Pac-Man. But what is that actually? That is actually natural log of 2 plus 2x log 3. I'll put the Pac-Man first. 2 log 3 plus 3x squared log 4 all times 2 to the x, 3 to the x squared, 4 to the x cubed. Now admittedly, that is the answer that I wrote on the quiz because I was being lazy, but it's also the answer that automatically comes to you from the process of log differentiation. Shall we try another? Suppose we've got y is the cube root of, I don't know, cosine of 2x divided by, I don't know, x square root of x times the, we haven't done this one in a bit, hyperbolic tangent of x. A little bit more. Let's throw in a 10 to the x squared minus 7 for good measure. There you go. That's pretty horrible, right? If you were to differentiate this directly, you'd have to do the quotient rule. But then you'd be met with the unpleasant realization that in the quotient rule, when you differentiate the denominator, depending on whether or not you do algebra, you'd be differentiating either the product of 3 things or 4 things, right? So what should we do? Well, we're going to do logarithmic differentiation, right? Because this is log differentiation day, so let's do that thing. So step number 1, step number 1's done. I already wrote y equals the thing. All right. So then what? Can you guys write it out for me? Simplify. See what happens here. We get natural log of y equals to 1/3 natural log of the cosine of 2x minus 3/2 natural log of x minus the natural log of the hyperbolic tangent of x minus the natural log of 10 to the x squared minus 7. Now, I'm going to put up here one more step just so you guys understand what I just did. So first of all, the upstairs one is really cosine of 2x to the 1/3 power, right? And what happens when you multiply x times square root of x? You get what? X to the 3/2. And then, of course, we've got our hyperbolic tangent, and we've got our 10 to the x squared minus 7. Suppose you don't remember the derivative of tanh. What could you do? Suppose you forgot how to... So show of hand, who knows what the derivative of hyperbolic tangent is? For sure, right now. Jordan knows. Cool. Other people not sure? You need to look it up?
I might be right.
You might be right. So because like, if you don't know, you could also do this, right? Because tanh is actually, you might know, I gotcha. It's the sinh over the cosh, yeah? So if you don't know what to do with that, you could trade it for like a log sinh minus log cosh. And I'm just gonna be an optimist and say everybody here knows the derivative of sinh is cosh and the derivative of cosh is sinh, right? I did say two different things just now, right? Okay, good. Sometimes I would say like the same thing twice, and that would be bad. But I like Jordi, I remember that the derivative of tanh is actually hyperbolic secant squared x. That is actually what happens there. So we'll use that. My point is if you didn't know that, you could unravel the tanh as the difference of logs in this world. All right, so let us differentiate implicitly. We get 1 over y times dy dx is equal to, well, let's see, we get a minus 2 sine of 2x divided by 3 times the cosine of 2x. And then minus 3 over 2x minus hyperbolic secant squared of x divided by tanh of x minus 2x divided by 10 to the x squared minus 7. So word to the wise. Well, anyway, a word. Let's see here. Word to your mother? No, that's not good. We don't do that anymore. It's from another time. So d dx of 1 over u, I recommend, oh wait a minute. My bad. Not that one. So sorry. d dx of the natural log of u. I like to think about the formula like this. It's du dx up here divided by u down there. I wrote the formula a different way over there on the left board, right? I said the derivative of log u is 1 over u times du dx, and that's not wrong. But in terms of formatting and bookkeeping, it's nicer to write the du dx in the numerator. That's what I've done. See this right here? This is actually how I package the formula. See that? So like 1 over cosine 2x, right? That 1/3 just rides along, it's still there. And upstairs, I've got the derivative of cosine 2x, which is minus 2 sine 2x. Here, the derivative of log is just 1 over x, so there's 3/2 times 1 over x. It's not interesting. Here, the derivative of tanh is secant squared, so I put the secant squared as the numerator, and I divide by tanh. That's the chain rule for the log. And here, the derivative of x squared minus 7. Uh-oh. Oopsie. Oh, come on. Dude. Well, one of these things is wrong. Seriously? This is sad. This is sad. What should I have done? Goodness gracious, guys. I can't believe I did this. This I should write as what? X squared minus 7 times what? Natural log of 10. That's the whole point. That's the goodness here. All right, so what I should have, see, and I didn't do this correctly. When I did the chain rule, I should have got what? I should have had 2x times the natural log of 10 times 10 to the thing. So if I'd done this correctly, the last term should have been, what I had written there, I just erased as wrong. So here's what it should be. 2x, my bad, it's just 2x natural log of 10. That's that last term differentiated. All right, so finishing move here. We got dy dx equals to, and I guess we could simplify that. Like that's what, 2/3. I tell you what, I'm not going to simplify it so you can see what I did. If I simplified, you might lose track of what I'm doing. So let me not simplify. So I've got sine of 2x divided by cosine of 2x minus 3 over 2x minus hyperbolic secant squared of x divided by tangent of x minus 2x log 10 all times y, which is the cube root of the cosine of 2x divided by x root x, which of course you could write as x to the 3/2 if you wanted, but I'm just writing it as it was, same as it ever was. Let's see here, 10 to the x squared minus 7. And there you go, there's a derivative, woohoo! I dare say that not many of us could have done that differentiation correctly using the techniques that we learned before today, right? It would have been troublesome at least. Ah, I was close. I did get it off the slide once in here. It did happen, right? You guys were here. It happened in this class, didn't it? Yeah. You can testify.
You actually did it twice.
I did it twice? Oh man.
Yeah,
see.
one time it went straight to the finish line.
Oh, which one was bad? Oh man. Yeah, there was one. So was this class I hit it just straight from like an angle? Some class I hit it from like over there into the basket directly. Was this one? Okay. I wish I'd do that in physics. I need to gain. They don't respect me as much as you guys. If I could make some buckets, then I have their respect, you know. Sorry, my friend at church. He was our interim pastor for a while. He wants to learn to play basketball better so that he can play with Mormons to like witness to them and stuff. It just cracks me up. So he beat me at horse the other day, which is not really much to say, but yeah. I never turned the camera. Uh-oh. Over to here? Oh, that's bad. That's real bad. Really? Oh, man. Huh. Well, it's there now. Now I'm like, when did that happen? Well, who can say? Well, you guys are here. You guys are all that matter, right? Let's do another example. So the way things are going to go this week, guys, is like hopefully tomorrow I will finish whatever there's left to say about logarithmic differentiation and hopefully the other topics. So I'll probably just lecture tomorrow on the other topics as well. And then hopefully Thursday we'll have a breakout session again where I put problems up and you guys can try them. So I'll have you guys try your hand at the logarithmic differentiation on Thursday like we did last week, and because some of you have said that helped. So we'll see. Hopefully it helps. Let's see here, example 3. What if you're up against y equals to x to the x squared cosine of, I don't know, 2x. So, all right, up till this point, my log differentiation examples have been of the form, well, you could do it another way, right? You could just have differentiated, right? Like you might say, well, you don't really need logarithmic differentiation because, after all, you could just do product rule and quotient rule. And it's a little bit ugly, but you can get through it. But at this point, no, you have no choice but to use logarithmic differentiation for this one, right? And so what do? We've already got y equals ugly stuff. We take the natural log of both sides. We get natural log of y is equal to, I'll write it out this time, natural log of x to the x squared. I'm not using my lemma. Showing you. So then power property brings down x squared cosine of 2x times the natural log of x. All right? So there you go. There you go. Now this one, it just so happens that like the taking the natural log has not made everything into sums. The reason that we got everything into, like everything became sums in the previous two examples is because the, if we had a power function, its base was constant, like it was a 10 to the x, or but if you have both the base and the exponent of an exponential expression, if they're both variable, when you take the log, you'll end up with a product of functions of x. So you'll have to do a product rule after step 1. So anyway, we are where we are. So let's differentiate. Log y here. Differentiate this. How's it go? I mean, it's just annoying, but we can do it, right? It's a product of what? 3 things. So we do our triple product rule. We do a chain rule on the left-hand side. So we've got 1 over y times dy dx is equal to, let's see here. So we've got 2x times the cosine of 2x log x plus x squared. What's the derivative of cosine 2x? It is minus, what's that? Minus sine, and then chain rule multiplied by 2, right? So minus 2 sine 2x, but you're right, minus sine. Don't forget the multiplication by 2 because of the chain rule. And then derivative of log is 1 over x. So here I had to use the triple product rule. And so the answer is dy dx is equal to, you got yourself a 2x cosine 2x log x minus 2x squared sine 2x log x plus x cosine 2x, all, big parentheses, times my y, which was x to the x squared cosine 2x. There you go. And that's how you differentiate that kind of thing. Let's look at an easier one of these. That one's kind of hard. Let me give you a slightly easier example. Let's try to differentiate like x to the x cubed. Can we differentiate x to the x cubed? So well, let me let you guys catch up. Any questions about example 3 before I go on to example 4? If I get away from you and you need me to slow down, it is totally acceptable just to ask a question. Say, hey, I haven't caught up yet. Could you just hold on a second? You're allowed to ask that question, you know, in here. Not at all my, there are other classes where I would actually be like, nah, I can't really do that because we don't have enough time. In here, we do have enough time. I can't always say that, but I can say that here for sure. Okay, so step 1, we wrote y equals ugly stuff. Step 2, take the natural log of the equation. Because we don't know how to differentiate this otherwise. All right, I can't do the exponent calculation. I can't do the log, the power calculation. Neither the power rule or the exponential rule apply here, because it's neither a power function nor an exponential function. It's both. It is a variable base and a variable exponent. So like we have no rule, so no like canned rule of differentiation for this. We have to use some other technique, right? Like what I'm saying is, power rule is this. Exponent rule is this. Right? Power rule. Let's call this exponent rule. Although this one doesn't really have a name, but maybe it would be good to call it exponent rule. I'm going to call it exponent rule for the sake of this discussion, if nothing else. For the exponent rule, the variables in the exponent. For the power function, the power rule, the variables in the base. This is neither of those, so you can't just do both at the same time. That's not how calculus works. So we pretty much